Okay, welcome to your second video for Unit 1. I'm going to try to make this one go kind of quick. I'm going to be showing you something today that you have sort of seen, but sort of have not seen, okay? But it's actually one of the easier parts of AP Chemistry. All right, we're going to be looking at 1.2. We're going to be talking about something called mass spectroscopy. Sorry, I almost said a mass spectrometer, but mass spectroscopy or a mass spectrometer. So what's happening here is we would do a mass spectroscopy experiment to try to gain information about an atom. And what it really tells us is, does the atom or element have isotopes? Okay, isotopes, this should be a review, but isotopes are like when you have the same element, like for example, like carbon, but the isotopes of carbon would all have a different mass. So like you could have carbon 12, carbon 13, or carbon 14. What that means is that carbon can be found multiple ways in nature. One is going to be found more abundantly or more often than the others. It's going to be more common. They're all carbon. So they all have the same number of protons. Okay, and PT would be like an abbreviation for protons, but they would differ in their number of neutrons. Okay, remember mass, this is all about mass, comes from the nucleus, and the nucleus is protons and neutrons. Okay, so if carbon can have a mass of 14, then we know that that nucleus has different numbers of neutrons in it than like carbon 12. So if you look at the periodic table, the atomic number of carbon is 6. So remember, that tells you the number of protons. So carbon has 6 protons. So carbon 12 has 6 protons and 6 neutrons. It's got to equal 12 for the mass. Carbon 13 has 6 protons and 7 neutrons. Carbon 14 has, again, 6 protons, and now it has 8 neutrons because it's got to equal 14 for the mass. They all have 6 protons. Remember, if you change the number of protons or you change the atomic number of an atom, it's no longer carbon. Okay, like if I now had 7 protons, I would be nitrogen. Okay, now, the way that a mass spectrometer works, it has to do with like shooting per se, like a ray or like an electron beam through this machine, and then there is a deflection, or like a deflection has to do with like a bouncing off kind of thing. So if the mass is higher of what is like being deflected, then it's deflected the least. If the mass is like lower, then it deflects the most. And so we measure the deflection. And so what happens here is a graph would be given to us, and the deflection would be given as what's called like signal intensity. We also sometimes see this y-axis reflected as percent abundance. Okay, it's basically like how many how much of the element that was tested had that deflection, or how much of that element had that mass. Okay, because the more massive particles will be deflected less. So we know that protons and neutrons are what the mass are made out of. And remember, I told you they're sort of equal to like 1 atomic mass unit. It's really like 1 point something, 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 something. There's lots of decimals. Now, we don't look at electrons for mass. They weigh less than a proton or a neutron. But when you get this signal intensity or percent abundance graph, what this tells you is that like 75.77% of the time, this element had a mass of 35, and 24.23% of the time, or less often, then the element was present with a mass of 37. So we would get information from this graph, and here would be what I want you to write down. First, you would see that there are 2 peaks on this graph. So that means there are 2 isotopes, or 2 ways this element could be found. So it tells you the number of isotopes present for an element. You also see the atomic mass of each isotope. In this case, 35 and 37 would be the two masses where the peaks are. And then you can see the relative abundance. Abundance is how often something is found, the relative abundance of each isotope. And that would be those percents, 75.77% and 24.23%. So this element is found in nature more often with a mass of 35 versus 37. Once you get this data, you can do what's called a weighted average to get the average atomic mass for an element, okay? Now, we did this in honors. I don't think that you do it in CP, but here's the deal. You do this all the time. A weighted average is the same way that you try to figure out your grade in the class. So if you know that you have like a 92 in the test category, and those are worth 50% of your grade. And then if you have like an 88 in the quiz category, and those are worth 30% of your grade, and those are worth 30% of your grade, then you do that. And then if you know that you have like a 100 in the homework category, and that's 20% of your grade, when you add up all that, it tells you your class average. It's a weighted average. You're taking each grade and multiplying it by the weight, like 50%, 30%, 20%. But notice I turned those percents into decimals. So you must turn your percent into, oh, that's not spelled right. Hold on. Oh, I know what I did wrong. I just did that. I was wondering what I did. You must turn your percents into decimals. How do you do that? You divide them by 100. By 100. Okay. And if you didn't know that, you got to be careful about that. I'm going to show you one in a minute where it's kind of tricky. Now, this thing right here means sum. Okay, get used to that. You're going to see it a lot this year. It's the sum of, because like sum means adding. So it's the sum of these relative abundances times the mass. And you don't want to round. Remember, 2 to 3 decimal places all year. So if I want to use that graph I just did, I would say, okay, 75.77% of the time into a decimal. I'm just dividing that 75.77 by 100. 75.77% of the time, the mass is 35. Plus 24.23% of the time as a decimal, the mass was 37. I'm getting it from that graph, those peaks. Add that up and you would get 35.4846 AMUs. How do it was AMUs? I'm just going by the x-axis, whatever they did. If they did grams, great. If they did AMUs, great. I'm just copying it. So the average atomic mass of this element is 35.4846. Shouldn't it be closer to 35 than 37? Absolutely, because 35 has more abundance and more weighting. It's just like your test category pulls more on your grade because it has a higher percent weighting. So look at this one. This one's the same thing, but the peaks look different. You're still going to see here that it shows relative intensity or isotope abundance, and that these are percents. Okay, this is where I was saying it's going to get crazy. You got to do 0.01% into a decimal. So that's 0.01 divided by 100. You're going to see in a minute how that gets a little hairy. Okay, so you got to make sure, even if it's already got, I'm trying to put a decimal point there. If it's already got a decimal, you still got to multiply, divide it by 100. Now, this is mass over charge. Z equals charge. The thing is that the charge is usually 1. Okay. You can dig deep into how a mass spectrometer works. You don't have to understand that. The Z is usually equal to 1. It's how the machine works. What I want you to think about here is that if you see relative abundance and mass mentioned on these graphs and these charts, you're not worrying about the x-axis having a z. Nobody cares. It would be just like if the mass is 39 over 1, which is still 39. Okay, you can see here that the mass of 39 is the most abundant. Now, because there is a percent here, that means there's a little bitty amount here for a mass of 40. Okay, that can be kind of tricky, so hang in there with that. But basically it says here, give me the average atomic mass. I'm going to do the weighted average. I'm going to say 0.9326% of the time, the mass is 39. I'm getting that from the x-axis. 0.0001% of the time, the mass is 40, plus 0.0673 times 41. Where'd I get that? Right here. And I'm getting that 6.73 up there, divide by 100. So 39.1347 AMUs. Now, they didn't tell me it was AMUs, but I would have assumed it was AMUs. You probably would have got the point if you put grams there. If this was an AP question, they probably would have actually told you that this is AMUs. Okay, that's the average atomic mass. I just did the weighted average using the peaks and the percentages and made sure to put the percentages as a decimal. Now, careful moving decimal places. Put it in your calculator and divide it by 100. What's the identity of the element? Okay, well, go to your periodic table and see whose mass is closest to 39.13. And you're going to see potassium. And then it says how many protons and neutrons would the most abundant isotope contain? Well, the most abundant isotope is a mass of 39 right here. Well, potassium always has 19 protons. That's its atomic number on the periodic table. That never changes. And 20 neutrons then would be the answer for the neutrons. Why? Because this has got to add to 39. Why? Because that's the most abundant. Now, again, the 19 protons for potassium never changes. If it's 20 protons, then now I'm calcium, or 18, now I'm argon. The number of protons of an atom is like its name, and you can't change it, okay? Now, this one is a little bit different. It says, hey, I've got rhenium. It's rare. It has alloys associated with it. We'll talk more about those later. It's a mixture of metals. The average atomic mass would be 186.21. I got two isotopes. Calculate the percent abundance. Okay. This is solved by doing what I would call like a system of equations. Okay. Now, you're going to learn this year. I don't always know the terminologies for math. Just because it's been forever since I've been in a class where the vocab has been used in that way. But I believe this is called a system of equations. Now, what am I talking about? This time you've got the average atomic mass. And you do have the masses, okay? This is saying rhenium with a mass of 185, and they're giving you the actual mass, because sometimes, like when I say carbon with a mass of 12, you'll see it written like that, like with a dash, and they put the mass after the element. But they'll do the whole number when they do the dash isotope notation, but they're still going to sometimes give you the exact non-rounded mass, and you want to keep as many decimal places throughout the problem as you can. But they're just giving you that other way of writing rhenium with a mass of 185 or 187, with putting that dash and then putting the mass after the dash. So remember, you always do the percent abundance times the mass. Okay, well, the mass is 184.95. I do not know the percent abundance. I'm going to put an X there. Remember, it's always adding up the relative abundance times the mass, like you do your classwork grade and your quiz grade and your test grades. So over here, 186.96 is the second mass, and I will do a raised dot for multiplication. I don't know his percent abundance. Okay, that would be my other unknown. Why? Okay, when you do a system of equations, what you're saying is that you understand that x plus y could equal 1, like a whole thing. And we know that we can say x and y equaling 1 for these two variables, because we know that whatever the percent abundances are, they would equal 100 or like 1. Like there's only going to be 2% abundances for this element, okay? And that the two relative abundances or percent abundances would have to equal 100% when it's said and done. So you could then say, okay, well, let me try to get this down to having one variable, okay? So if you wanted to say like y equals 1 minus x, okay? Then you could come down here and do this. 184.95 multiplied by x plus 1 minus x times 186.96. Now, you're going to have to be like good with your algebra here. Writing more is probably going to help you than writing less. But you're going to have to remember that you're going to have to feed in or distribute the 186. So you're going to have the 186 times the 1, and then subtract or minus 186.96 times x. At the end of the day, when all is said and done, you're going to get x equals 0.373. Now, if you, especially if you're a junior, I'm going to beg and plead with you to try to solve that on your own, in your own way, to make sure you get x equals 0.373. And if you don't, you got to shoot me an email and we got to catch you up math-wise. Okay? Now, you've only solved part of this. You've got to then say, okay, that means 1 minus 0.373 is y, or 0.627. And then you've got to remember that those would have been percents that you had divided by 100 to get them into decimals. Okay, so then the actual answer is 37.3% for this isotope. I'm multiplying it by 100 to get it back to a percent. And 62.7% for the rhenium that has a mass of 187. Now, a couple of things. Yes, I'm going fast. Class goes a little bit slower than this throughout the year. So if you're like, what in the world is happening? That's okay. Because some of you need me to go fast, and this is pretty easy for you. Some of you right now are probably needing to slow the video down or maybe go back and watch parts of it again, rewind and replay. And that's okay too. That's the beauty of you being able to do that. But if you're drowning already, you got to reach out to me and you got to go back and rewatch this. Remember, there's slides under Unit 1. Right now, you're going to do the additional practice questions, and then you're going to check your answers and notate if you need any help. And I'll be back shortly to do 1.3.